Welcome to week 11 of the cs102 Further Computing. My name is Götz Pfeiffer and this video is about visualizing higher dimensional data. That's like three-dimensional or even more dimensions, and naturally it's more of a challenge to plot or visualize such multi-dimensional data in a two-dimensional drawing. That's what a sheet of paper is after all, or what a flat screen is after all, despite all efforts one might make to create a three-dimensional impression. And here we're going to look into what the matplotlib package offers by the way of creating higher dimensional illusions or taking advantage of whatever is available in two dimensions. So as usual, we start by importing the packages we're going to use and then look at a couple of different ways to add a dimension or to plotting a set of data. We start by looking at contour plots. That's something you might know from maps, walking maps in particular. They indicate not only the locations of things, attractions in the plane or in the region that is mapped out on the map, but sometimes they also have these height information, which is useful for, well, hill walking, in the form of contours, so lines which trace out a constant height across the map. That's the idea here. And there are various ways in which this can be accessed, such a feature, through the matplotlib. There are in particular three functions that are helpful for such a kind of plot. That's the contour function in the matplotlib pyplot package, which we as usual abbreviate as PLT. Then there's a function contour F, where I believe the F stands for fill or filled. So this is for filled contour plots. And then there's a command imshow for showing images. And we'll see how this works in examples, specifically in the example of a function of two variables. That might be of interest for two-dimensional analysis or even complex analysis. Looking at the values of a function that depends on two input parameters, x and y, rather than just one. So here we'll work with the following function, defined as the sine of x to the power 10 plus the cosine of 10 plus the product of y and x times the cosine of x. A function in terms of x's and y's that uses trigonometric functions, and it uses in particular the efficient implementations of these trigonometric functions in the NumPy package. So here the x's and y's are, I guess, not single numbers, but they're arrays of NumPy arrays of values to be fed into this function, so that this formula can be evaluated all at once on the entire set of x's and y's, or pairs of x's and y's rather. So in this sense, the contour plot that we're going to create will take three arguments, namely a list of x values, or as we'll see, rather a grid than a list, in a similar way, we'll pass the list of y values as a grid, and then corresponding to that we'll pass a grid of z values, which will be the values of this function evaluated at a particular pair of an x and a y. And of course the x and y values, they represent positions in an xy plane, and as such they will be represented as positions in the plot, and we'll have a z value for every combination of any x with any y, and these z values will be represented as contour levels. So in this sense the x's and y's are input parameters, and z is an output parameter of this f function, which then is the third input into the contour plotting command. So we start in a way that we might started before, setting up a list of x's, 50 x values between equally spaced out between 0 and 5, and similarly 40 y values equally spaced out between 0 and 5. Let's look at one of them. So y, there they are, 40 values starting at 0, ending at 5, and between them, so that it's in total exactly 40 equally spaced out, another 38 values. So this gives us 50 points between 0 and 5 in the x direction, 40 in between 0 and 5 in the y direction. That's a total of 200 pairs on which the f function is to be evaluated. And now in the NumPy sense, in an efficient sense, you want to allow NumPy to work on x's and y's simultaneously. In particular, here the product of y and x should be evaluated in the NumPy way efficiently, which involves, as you might remember, broadcasting of either one or both of them into shapes, so that the x's here together with the y's do actually represent points in the plane, rather than pairs to be evaluated in parallel. So for this to work correctly, for the broadcasting purposes within the f function, I guess we would need to reshape the y to actually be a column vector rather than a row vector as it is here in the coming out of the linspace command. So that's why it here says y.reshape 40, 1. And then we can apply f to x as a row, y as a column, and get a combination of z values out of that. Let's see. So this works, and let's have a look at the z that comes out of it. So this is a two-dimensional array of values, one for each pair of x's and y's, I suppose. But then this is a bit verbose, a bit I mean, it works, but it's not nice. So maybe a cleaner way to work with this situation is to use a function that is there for this purpose in the NumPy package. It's the mesh grid function, which takes one-dimensional arrays as input and builds the corresponding two-dimensional grids as output. And that's so we apply the mesh grid to the little x and the little y, which are both lists of many values, and what we get back from this, we call it X and Y, and capital X and capital Y, and these will be the broadcast versions of X and Y, just in the sense as we discussed this previously. And then we can apply our function f to X and Y, which now are grids, and evaluate this to capital Z, which should give the same result as before. The same result as before. It gives the same result as before, trust me. But now we're not here to compute these values, we want to see them as a contour plot, and for that purpose we feed them into the contour command of the package. If we do this with the little x, little y, little z, this works, and it gives us a contour plot. You see along the x-axis values between 0 and 5, along the y-axis there's values between 0 and 5, and the z values here are represented by these contour lines, where, I guess the same z value across this picture uses the same shade of gray. Here it doesn't tell us what actually the z value is. Doesn't even tell us whether this goes down, up or down. This so there could be more information, but that's basically the idea of it. These are the data computed from the x's and y's are turned into contour lines representing the z values. And one can work with this in different ways. We can, the preferred way actually is to use the capital X, Y, and Z versions of the same data. Capital X, Y obtained from the mesh grid applied to little x and y. And then we can, for example, ask for a specific color, blue, say, and then we get a plot of the same data. This confirms the fact that the capital versions of x, y, and z actually do carry the same information as the little x, y, and z. But we'll stick to the capital ones from now on. Blue, and here it's a single color. It's no longer gray scales or blue scales, as it were, and maybe you don't need the scales because as you move out between these contour lines, of course, there's only one way to increase or decrease. This is somewhat self-explanatory. And the additional information you get here is that negative values of z are represented by dashed lines. So you actually see in this plot that these islands here are valleys, and these regions here are hills in this plot. And of course we can ask for more color. We can ask them to apply a color map in some way. The red-gray color map sometimes makes sense, abbreviated as RDGY. Also, we can ask explicitly for 20 different levels of 20 different z values to be indicated as contours, and then we get a picture of this kind. It still describes the same landscape. Now the valleys are red and the hills are gray. We have more contour lines than we had before, so there's a bit more detailed information, and gives an impression. The human eye is very good at reading such data. Maybe one can even improve on that. There are There are other choices of color maps which one can find in the documentation under the plt.cm module, and for still a better plot we move on to the filled contour plot, which gets rid of the spaces between the contours here in a nice way. So for this we use the contour F command, F for filling, which apart from that works very much in the same way as the contour command. And I think we've done this before. We can add a color bar to the plot to provide a legend, an explicit correspondence between the colors being used and the actual values these colors stand for. And then you get a filled contour plot, which looks like this. Again, the valleys being red, negative values redder and redder. The hills are gray, and this is like, it's not really smooth, but it's rather than plotting the contours with a consistent color, the contour lines, what they plot here is the regions between between the constant contour lines with the same color. And with the color bar you have the explicit information what the actual values, the Z values are that are shown here. So that's nice. And then as an alternative is to create an image from the data. That's of course something you can do. You have the positional data, the x's and y's, and then for each x and y you have a z value which is here interpreted as a color value, and the imshow command works a bit differently. It takes the this one takes the grid of z values. It takes an explicit keyword argument that indicates the range of x's and y's that these z's come from. It uses the origin keyword command to set the 0 point to the lower left, which usually when working with pictures the origin is on the upper left. And again we can ask for a color bar, and then we get this pixeled version of the same information. This time it's not the lines of constant value that are being traced out. This time it's for each pair or each, say, little square between two x and y values. There's a color attached to it which is derived from the z value that is achieved somewhere on that square. Third possibility. So this, as I said, it works a bit differently. It doesn't work on the x and y grid, just from the z values itself. And then there's, as usual, lots of flexibility that comes with all these drawing commands. One thing one can do is one can draw one type of image on top of the other to make them shine through. It helps to set the alpha value, set some transparency via the alpha value, and there we get, for example, on top of an image that shows things in between red and gray, using the red-gray color map with transparency 1/2. On top of that we draw the contour lines, and we can also use the C-label command to label the contours. Here we have labels 0, 0.5, or rather minus 0.5 or 1.0, indicating what values the contour lines correspond to. That's the that's various ways of making contour plots of three-dimensional data, attaching a z value to every position in an x-y plane, using color or the contour lines to indicate the z value. Now, proper three-dimensional plotting is of a slightly different nature, right? So for this we have to explicitly import an mplot 3D package from MPL toolkits that then allows us to create a three-dimensional axis object with the usual axis command and the keyword argument projection set to 3D. Oh, there you go. This is, rather than your XY plane, this is a three-dimensional rendering of an X, Y and Z plane. Again, by default, all three ranges between 0 and 1. Nice, isn't it? But there's more. We now can plot three-dimensional data into it, but we can also take advantage of the functionality that comes with the notebook, or the fact that we're not reading a printed book, but we're working on a live computer. What I mean is we can make these three-dimensional figures interactive. Here this is done through what was called the magic command, the IPython magic, starting off with a percent symbol, and if we set the matplotlib magic to notebook, we get an interactive 3D axis object like this. So this is not only bigger, it reacts to my mouse. I can use the mouse, so I need to click and mouse to rotate this thing, to look at this three-dimensional grid from all possible angles. Nice, isn't it? So let's use this. Let's do a three-dimensional drawing. Let's draw a trigonometric spiral together with some points, some random points near that spiral. So that's a well, here it is explicit, and here are the data. The z coordinates is linear coordinates between 0 and 15, 1000 values. Then in the x direction we take the sine of that value, and in the y direction we take the cosine of that value. So seen from above, this traces out a circle, but since the z value is moving upwards, it creates a spiral in that 3D space. Then with some random distortion, we create some data points, discrete data points, which we scatter with the scatter 3D command along this line. And that gives a picture like this, which again is interactive, and I can rotate in all sorts of ways. As I said, seen from above, this is a circle with some dots drawn randomly near this line, and the darker they get, the higher this is. I've turned it upside down now, sorry. How can I? Maybe like this. Or is it deep? Anyway, that's one way to play with three-dimensional plots. So if I can, I think I better switch this off. Otherwise it's eating all my resources. So I didn't ask for this implicitly. These scattered points, they use transparency, changing alpha value over time or over the z-axis to give a sense of depth in this drawing. And with the interactive features, you get a really good impression of these three-dimensional data. It's also possible to make three-dimensional contour plots, and for that I'll switch the matplotlib back to inline to illustrate the various features. And I'll be skipping over details here. I just want to show off what can be done. If you develop an interest in the details, you might want to scroll through the notebook in slow motion and discover the details for yourself. That's probably a better way to work with this than me explaining every little detail. Now we've seen how one can access the documentation. There's some links at the bottom of this notebook that you can follow. And if you want to know about the details, follow those links, look into the documentation yourself, and try things out yourself. And you could get plots like the following. Here we're looking at z values computed as the sine of the square root of x squared plus y squared. And that gives in the standard contour plot with the binary color map, gives a drawing like this. That's the sine of the square root of x squared plus y squared. The sine of the length of the vector pointing from 0 to xy. And that's the contour plot again, plotting now in a 3D fashion lines, solid lines standing for a constant z value along this line, which here take the shape of circles. Now, you're really talking about a surface, and there are different ways to indicate the surface in this 3D drawing. And if you want to make this interactive, you can switch the matplotlib magic back to notebook, and then you can look at this from all sides. Here's a so-called wireframe, which isn't contour lines along constant z values. This is rather the underlying xy grid projected onto the surface of z values, and that's a different way of creating a visual impression of this three-dimensional data. So here you're coming from the square grid of x's and y's, but there are generalizations of this, and one can use any kind of polygon to map out the surface that is the collection of all the z values. Here's a surface plot with certain parameters, the viridis color map that we've seen before, and that gives a more solid picture, which has advantages, but also it has the disadvantage that you can't see through. You can't really see all the parts of the 3D plot. And Now, this still comes from a rectilinear underlying grid. There are more interesting patterns. And here's a pattern that is a grid that is better adjusted to the surface being plotted, and sometimes it's appropriate to use triangulations of the surface, incorporating sometimes random points, random decisions. So here's a surface plot coming from a triangulation on the basis of these are, first of all, these are some random points chosen in the xy axis, and then the function is evaluated at these random points, and they are like a scatter plot, and this is a three-dimensional scatter plot using a color map to indicate the z values. This is what's specified here. Z makes the color of the plot on top of the three-dimensional drawing, just random points. But that's if you really want to plot a surface, that might not be appropriate because there's too much gaps between these points, and that's even less information than the grid lines in a mesh or the contour lines in a contour plot. So that's where a function like the plot try surf might be useful, which finds triangles between adjacent points. The random point, the same collection of random points here, any three of them can be joined up by a triangle, and then the face formed by the triangle is colored. That gives a that gives a solid colored plot of the surface, which isn't restricted to the regularities of a square or rectilinear grid. And that's that's an example of the flexibility that you get from introducing random elements, random choices into your plot. And to finish this off, we plot a Möbius strip using these techniques into 3 dimensions. A Möbius strip is like a strip of paper glued to form a ring, but with a half twist before you glue it. It's an interesting topological object because topologically it has only one side. You can walk around the thing and without crawling over an edge you end up on the other side. So here we use a certain parameterization to use the matplotlib drawing facilities to create such a Möbius strip. So the leading parameter here is the parameter theta, which ranges from 0 to 2 pi once around the circle, and then we have another parameter w, which ranges from -1 to 1 across the width of the strip, or rather -1/4 to 1/4. We can, as before, turn the pairs of thetas and w's into a mesh grid and calculate the z positions from it. There's the formulas, and I leave the details to work through to you. There's an ravel function from the NumPy package being used to compute actual x, y, and z values from theta, an angle phi, which is half of theta, and the w parameter. And then we can import from the matplotlib package a triangulation function which does the triangulation business, and then when we plot the Möbius band, we get an image like this, where again I've activated the interactive features of the notebook, so I can turn this around, and you can maybe follow this visual impression of a paper band wrapped around runs around the circle, but it has this twist which makes it join up upside down with the other side. And maybe we can try and walk along the surface and find yourself walking from the inside here once around the circle, ending up on the outside of that Möbius band. So that's that's a brief glimpse at the 3D plotting facilities, at plotting facilities that allow us to plot three-dimensional data either as flat contour plots or as actual three-dimensional plots with various ways to actually draw the surface in question, and also with the added luxury of having this interactive as part of the Jupyter notebook. So that's that.